How long do I have to write for the IA usually?
About 11 to 12 pages, about 2,000 words.
Oh,
Less than 2,500 words. Okay.
okay.
12 pages. For example, this one has 7 pages. Not necessarily long, like 12 pages. It could be 9 or 8. Could be 10. Yeah. Many other students did it with 11 pages.
Okay.
The sine is lambda over d. So this is the difference between the sine and the tan. About 14%. This is sine. Lambda over d. The path difference is approximately d times sine theta, and at the first maximum, the path difference is one wavelength, d sine theta equal one wavelength, and therefore sine theta is approximately lambda over d, and we compare it with the tan theta, okay, which is the separation over the distance. We want to verify this equation, and we cannot measure the angle directly because it's too small. Therefore, we measure these two things so that we calculate the tan and see if it is approximately equal to sine theta. Okay, and the percentage of error is about 14% as calculated here. Okay, 14%. And so if you can repeat the experiment other times with higher order, second, third order, and at meaning greater angle, you see that the greater angle, the difference here become greater. Okay, therefore at lower angle, small angle, like the first order, this is a good approximation. Okay, the ratio. Write about the error, explain how you get to the 14% error here. So just follow the step in this document, okay? But use your own language and your own result.
Yep.
The difference between the two is rather small. Okay. The error introduced by the small angle approximation larger for short L. You see here, short L, 19%, 22%. And then for greater distance up to 9.5 meter, that is unbelievable. 9.5 meter, a very powerful laser and a very big room, like in a sport room, so that the distance can up to 9.5 meter, and the error becomes smaller. But in your result, only in less than 2 meter distance, you get the error 14%. That's very good.
But there is still like 3% difference.
Okay, that is the unavoidable. Cannot change that because it is the difference between sine and tan. Okay, we can like compare the sine and the tan different. For example, the angle is 0.2 degrees, 0.2 degree. But if the angle, I assume the angle to be 1 degree, okay? 1 degree sine is this value. And then I subtract it with tan. Here, this is the difference. And then divide it by sine of 1. And then multiply by 100. And yeah, very small difference. This is lower than only very little difference, for 1 degree. So it means that the calculation, the error here is not because of the difference between sine and tan, but random error, other factor that we didn't know exactly the reason why, but quite a big difference. Let's say if this has some assumption about the difference. This is due to the fact that the trajectories followed by the laser beams from the two sources are approximately parallel for larger distances L. This beam from two sources are approximately parallel for large distance L. No. If like you still have time, you can repeat experiment like measuring the distance between 6 or 8 separation instead of only 2. Okay, therefore you can increase the accuracy of the separation. 1, 2, 3, 4, 5, like measuring 8 separation and then divide it by 8 to get more accurate separation.
Yeah.
Okay. Yeah. Let's see if we can find another report, but it's okay. It's even when you have like big error like this, the point understanding the principle, the procedure of experiment, the theory, and be able to explain the reason of the error, and you still get good mark, not necessarily to be very accurate result, very low percent of error. Okay. 2 other students of mine got very good mark with errors in the experiments.
I think like other students have also a lot of error.
Yeah, they're allowed to make errors as long as they understand the theory, the procedure, experiment, can explain, analyze the result, and explain the cause, the reason of that error.
Oh, okay.
Okay, so we just linear fit our data. And how about the linear regression line here? We see this coefficient 0.37 is approximately equal to the tan, right? The tan and fringe separation. So the equation for the fringe separation S equal lambda big D over small d. So it is lambda times small d over big D is the, okay, this is slit separation. Lambda over D is calculated. Obviously we can replace the letter D here by L. Okay, lambda over D. This ratio is 0.0034. And our linear regression value is 0.0037. Okay, just a little bit different. 0.0037 minus divided by 0.0034 is only 8% different. Okay, 8.89% different. Yeah, this coefficient. Okay, write it down in the graph here. Insert equation. The coefficient, the gradient of the linear regression. The gradient of the best fit line is 0.374, which is different from the ratio of lambda over D equal 0.034, and we also need to mention the uncertainty here, plus or minus something. The value of the gradient here, we can also find the absolute uncertainty by drawing two worst fit line, okay, and find the gradient of those two worst fit line. I will insert the worst fit line and về mới. Yeah, I insert the worst fit line. Oh, I need to insert the error bar first. For the error bars, out element error bars, standard deviation, that it could be too big, huh? How about like percent? Error bars, 5%. 5% is approximately still the same with the standard deviation, okay? Error bar by using standard deviation. So we see that the error bar is very big, okay? Is there like any? I can increase the scale here to make it like smaller error bar. Exit the value, change it. Option, no. Exit option, minimum like 70. So that it looks like it's smaller error bars, okay? Minimum 2. There. See? 3.
Yeah.
3. Here should be like 80. There. Just let's increase the text size. Increasing the text size here. 11. I don't know why if this looks so weird here, the text. Okay, it's better. Okay, much better now. This is the error bar with the standard deviation, okay? And so we can also insert the two worst fit line. One worst fit line pass through the top and the bottom, okay? And another worst fit line should be in another color or used like dash line. No, it should be just that, but we can change to another color, blue color. We are allowed to use different color, right? Another worst fit line here, pass through the bottom and to the top here. Okay. Then let it too dim. Oh, okay. I will draw it on the Excel and then copy to the online drive, online doc. Here, one worst fit line. You can change the color, shape, weight, change it to like this color to distinguish from the best fit line. And we can also change the worst fit line, the best fit line, the linear regression line to be solid, where to format it. Dash line is a straight line like this, okay? We can make it bigger to emphasize its importance, okay? This is the equation of the best fit line. Then from the two what's fit line here, okay, you can calculate their gradients, maximum and minimum gradients, okay, like this. Where is it? Yeah, it's the Word document here. You have two what's fit line, okay, and then you calculate maximum gradient and minimum gradient of the two what's fit lines, okay. This thing has the greatest gradient, okay, and the other one has the lowest gradient, and from those two greatest maximum and minimum gradient, you find the average gradient, which is the ratio. Approximately, we compare it with the ratio of lambda over d, okay. Uncertainty gradient, the maximum minus the minimum, and then divided by 2, so that you can mention the uncertainty here, plus or minus something here, okay, plus or minus the gradient, okay. And also this thing, we also need to calculate the absolute uncertainty. Absolute uncertainty by using this uncertainty of wavelength. So the percentage uncertainty of this ratio, lambda over d, this ratio is 0.34, okay, but we want to find it plus or minus something, an absolute uncertainty, by calculating, let's call this is sine theta, okay. So percentage uncertainty of sine theta over sine theta equal to absolute uncertainty of lambda plus the absolute uncertainty of d, okay. This is 20 over 680% plus this d 0.5 millimeter over 0.2 millimeter percent, okay. So this is this more d, so the uncertainty of this thing, we don't know the uncertainty of d here, right, because we assume it to be 0.2 millimeter without knowing its uncertainty, okay. So we assume that this is to be like 5% uncertainty because we don't know exactly. We don't have the tool to measure this small tiny distance. To measure that tiny distance, we use this ruler, in distance, in thickness ruler. I don't remember the name of that tool. Here, this thing to measure tiny distance.
I know.
Caliper. Okay. Yeah. Caliper. We need a thing like that to measure the small distance, the width of the distance between the two slits, 0.2 millimeter, but we don't know exactly the uncertainty of that. So we must assume that to be like 5%, okay, or maximum 10%. 5% here, okay. And this is 20 over 680 and times 100 is a 3%. 3% here, 5%. That is 8%. Okay, so 8% is the percentage uncertainty of this thing, and let's take that 8% multiply with this value 0.0034. We get this value absolute uncertainty 0.808% times 0.0034, 0.00027, 0.00027. 0.00027. 0.0027, and we need to explain why we get that. Okay, using this. And here you find the line, the worst fit and the best fit, the gradient of those two worst fit lines. Okay, identify the absolute uncertainty. You can open this AI, which I sent you last time, to see the way to determine the uncertainty of gradients. Okay.
Yeah.
Let's take a screenshot here. Worst fit line, best fit. So with difference, we don't see it. How many percent? Assume that it to be 0.0037 divided by 0.0034. That is about 8.8% difference. By 8.8% difference, which is different. Okay. Best fit like worst fit subdivision. Okay. Conclusion. Agrees with the theory. It's a linear relationship. That's the most important thing. Conclusion. Good linear relationship. Good coefficient of correlation. Proving the linear relationship between the separation and the distance L. Systematically improve by increasing L. The slope of the graph is very close to expected value. Our slope is 0.37 and the expected value is 0.034. 8.8% different, which means it's close enough. The gradient is approximately equals the expected value of lambda over d. Looking for the equation lambda over d. 8.8% difference. Observe the formation of interference pattern. The aim is to determine whether the constructed interference equation hold. Fundamental assumption contained the fundamental equation is that the angle is small and the distance large enough, so that trajectory followed by line from the two sources are parallel. Okay. First paragraph is like unnecessary. Just repeated the idea of the introduction. Rearranging formula making is subject to obtain value of L, which is, what is this? Okay, so the value of L distance L. Graphical orientation ratio L with a linear showing the pivot graph value L become greater. The width is Y over L. That's very tiny, so we don't need to make this graph. The error introduced by the small angle approximation larger for short L and smaller for correct L up to 9.5 meter. Explain these errors. Okay, any explanation with the errors? Errors are almost like the same for these distances because the distance only changes like 30%, right? From 1 meter to 101 and 30 centimeter, 130 centimeter, and therefore not much change in the length, therefore not much difference in the percentage here. But if you like double and 3 times greater, then there could be more difference. Okay. So that's the thing that you can mention in the evaluation. The difference between the difference, okay, between the ratio lambda over d and separation S over L is about 14%. If we take the average, 14%. Okay, and just not very much compared to the change of the distance L, which is 30%. This proves the consistency of the relationship. Consistency of the relationship between the separation proves further improvement of the experiment with greater distances. Distance should be carried out to verify the validity of this approximation, the approximation small angle approximation. It's about 14%, which is not very big, not very large. Great. Not very big. Which would be large, big, great? Very large. Very much compared to the change. Okay.